Hello class, today we're talking about matrices and row operations. And we're going to be using these matrices to solve systems of equations. Now there's some operations that we're going to use to write matrices in equivalent forms. These operations are similar to the operations we did when we were solving the systems of equations in the previous section. However, we give it a new name under this method, and when we talk about solving the matrix, we want to write them in row echelon form, and sometimes we want to write them in reduced row echelon form. And so you need to know the difference between those two terms. And then we're going to be solving applied problems using matrices. Let's get started. Before we begin, I just want to make sure that we're up to date on some terminology. A matrix is a rectangular array of numbers, and each number is an element of the matrix. We're going to be using the matrix to represent the linear system of equations. So you can see over here that the linear system has two equations in it, and the coefficients are the only pieces that we bring into the matrix. So 2x plus 3y is equal to 7 turns into 2, 3, and 7. And negative 4x plus y is equal to 5 turns into negative 4, 1, and 5. So we write it without the variables and without the equal signs, and that's your matrix. And then to describe this matrix, we call the order of the matrix the dimensions given by the row by the column. For instance, this is 2 rows and 3 columns, so the order of this matrix is 2 by 3. Notice that the x coefficients are in the first column, the y coefficients are in the second column, the constants are in the third column, and they all line up nicely with each other. The vertical line represents the equal sign. And when we have the matrix written this way, we call it the augmented matrix. If we took out the 7 and the 5, and we just had just this portion of the matrix, that would be the unaugmented matrix. But we're always going to use the augmented matrix to solve the system of equations. Now you can see that the operations that we're using to transform this matrix are the same operations we talked about in section 11.2. That is, we may interchange any 2 rows, we may multiply any row by a non-zero constant, and we may add the elements in one row to the corresponding elements in another row. And the whole goal is to get it where there's 2 variables in our first equation and 1 variable in our second equation, or so forth. And notice that you have the leading coefficient is 1 for each of these. And when we write it this way, we call it row echelon form. When we put things in row echelon form, it's very convenient to solve the matrix or solve the system equations once we get it in that way. Let's see what that looks like. Let's look at some elements of a row echelon form matrix. First of all, we want the first non-zero element in any row to be a 1. We call it a leading one. And then all the elements below a leading one has to be a 0. And then you want to arrange it in that order so it sort of looks like a staircase of 1s. Let's look at the ones we have down here. Our first element is a 1. Everything below it is a 0. The next non-zero element in the next row is a 1. And there we go. We don't worry about the values in the other places. This is a 2 by 3 matrix. We would read it out loud as 1, 2, 4, 0, 1, 3. Just reading it in order, row by row, left to right. And we describe it as a 2 by 3. The order of this next matrix is also 2 by 3. It's 1, negative 2, 3, 0, 0, 1. So is this the same format as the one before it? It's not exactly the same, but it is still in row echelon form, because we would say it has a leading 1 up here, then it has a 0 under that, and then the next non-zero element is indeed a 1. As long as we have zeros before the 1, then we are okay. So this one still is in row echelon form. The next matrix we're looking at is a 3 by 3 matrix. It has a 1 in the leading position, zeros all under that. It has a 1 in the next leading position, zeros under that. And it has a 1 in the next leading position. And so once again, you can see the staircase of 1s happening. And the next one is a 3 by 4 matrix. Once again, we have a 1 in the leading position with all zeros below that. In our next row, the next non-zero number is a 1, and all zeros below that. And then the next digit is a 0, and the next non-zero digit is a 1. So all of these are row echelon matrices. For question 1, we're asked to use Gaussian elimination and matrices to solve the following system of equations. Now the first thing we want to do is write it as an augmented matrix. Notice I have these steps listed on your notes so that you can follow along when you try it on your own when you do the book example. Also, I'm going to label my lines so that way I know what I'm talking about. Now our next prompt says we want to have a 1 in the upper left-hand corner. And we can do it by following any of the operations that we're allowed to do. That is, we may interchange any two rows, we may multiply any row by a non-zero constant, and we may add the elements in one row to the corresponding elements in another. So the first thing I like to do is see if any of those leading coefficients is 1, and if it were, then I would just switch the location of that row so that the 1 is in the top row. But neither of these have a 1 in the beginning. So then the next thing we can do is multiply any row by a non-zero constant. And it uses the word multiply, but multiply and divide are the same thing. So for row 1, it looks like if I divided that 2 by a 2, then I would get a 1. So that's something we could do. Now if I decided to divide row 1 by 2, then I would have 1, 7 over 2, and 15 over 2. And that's completely fine if you want to do that. However, if you want to avoid fractions, then we could also go with a third option, which says we can add elements of one row to the corresponding elements in another row. Let me show you both options. Now, typically you wouldn't solve an equation in two different ways, but I want to show you the different options you have. Row 1 doesn't apply here because none of my rows have a leading coefficient of 1. So we can't do row 1. Row 2 is saying, hey, let's take whatever is in our first row and divide it by its first coefficient. So when I divide it by 2, I end up with 1, 7 halves, and 15 halves. Rule 3 says to add some rows together and make it so that when we add them, we end up with a 1. And so I took the negative of the second row and I subtracted the first row and I ended up with 1, negative 11, and negative 7. And so of these two rows that are able to come up with a 1 in the position we want it, which one did you like better? And it just depends. Sometimes you don't mind the fractions. Sometimes dividing might not create fractions, and then that's easier. But sometimes we want to go ahead and add combinations of lines together. That way we can come up with numbers that do not have fractions. So which one do you prefer? I think I agree with you. I hear a lot of people prefer this third option. Let's use that one. Now that we have that first position as a 1, we now want to make the position under that a 0. And so we don't have a 0 in that spot to be able to move in that spot. So once again, row 1 is not an option. We also cannot multiply or divide by anything to make a 0. So rule 2 is not an option. So the only option we have at this point is rule 3. We need to do a combination of adding these together to make that number in the bottom a 0. So I went ahead and wrote row 1 without any changes. And then for row 2, I added 3 times the first row to the second row. Now I didn't show my work. I'm writing what I'm doing in orange, and then I'm adding them up in my head or on paper or somewhere on the side or using my calculator. But I'm coming up with these numbers. Now if you need to show your work, that's fine, but for the matrices, we're just assuming that if you know the row operations and if you can get one to the other, that you're doing the correct work. I can tell you that if you're not very careful about your notation, what I'm writing in orange, if you make a small mistake, it's really hard to see where it came from. But if you write down your steps, then you can do this and then you can check your work looking at the matrix before. Don't erase it. Make sure you can look at it so that you can write down all the steps correctly. So remember, our first goal was to get this first coefficient of 1. Our second goal, after that first coefficient is a 1 is to get our any number below that a 0. So we might even do multiple rows at the same time. Then the next step is to get the next leading coefficient into a 1. So now the question is, can I interchange any rows? Can I divide or multiply by a number? Or can I add it to another row to get that to turn into a 1? And right now we're going to do Rule 2. Rule 2 says to multiply or divide to get that into a 1. Once I have it, 1 in the first spot, any zeros below that, 1 in the first spot in the second row, and any zeros below that if they existed, we're now done getting this into row echelon form. Now that we have it in row echelon form, we can rewrite it as a system of matrices. And the system of matrices should already be solved for the second variable, and so all we have to do is substitute that value into the first variable. Substituting ry is equal to 1 into that value, then we get x minus 11 is equal to negative 7. We can add 11 to both sides, and we get x is equal to positive 4. We've now solved for our x and our y values, so we want to put them in an ordered pair. And so now you have the solution as 4, 1. We're going to follow the same steps we just did to solve this system of equations in 3 variables. The first step we want to do is write it as an augmented matrix. Make sure to put 1s when it's just a variable with no coefficient, and to put 0s when there's no variable at all. This would be a 3 by 4 matrix. And so looking at the rules, which rule are we going to use to get a 1 in the upper corner? The easiest rule is, if there's already a 1 in the first column, let's just rearrange those rows so that the 1 is in the first position. So we're going to take that row 2 and put it in the row 1 spot. So you can see we just switched the order of row 1 and row 2, and now we have a 1 in that top spot. Now we want to make all of the rows under that have a 0 in the first column. And so we're going to do movements with 2 of these. And you cannot make things a 0 with anything except for the third rule. So we're going to apply the third rule and do adding to get that 0 there. So I have my work shown on the left in terms of what steps I did, but I'm not showing my work. I'm not actually multiplying it out. I want you to do that and see if you get the same results. So for row 1, I wrote the exact same thing as row 1, 1, 4, 2, 17. For row 2, I took the previous row 2 and I subtracted 2 times the previous row 1. And so that was 2 minus 2 times 1, 1 minus 2 times 4, negative 1 minus 2 times 2, and 3 minus 2 times 17. For the third row, I took the existing third row, and then I added 2 of the second row. So that's negative 4 plus 2 times 2, 0 plus 2 times 1, 1 plus 2 times negative 1, and negative 2 plus 2 times 3. So verify if you get the same answers, and then let's move on to the next step. That next step would be getting a leading 1 in the second column of the second row. Recall, we already have the 1 here, and then we put zeros underneath. Now we're working on this spot. To make that negative 7 into a positive 1, you could have divided everything by negative 7, but since that would have left us with some fractions for the rest of the row, I'm not doing that. I'm instead doing a combination of rows, and so I'm going to combine this never with row 1, because row 1 still has a value in that first spot, and we want to keep our 0 there. So we want to combine it with this row or any row beneath it. So row 2 will be combined with 4 times row 3. So now that we have a 1 in that spot, we want to make the number below that a 0, and any other number below that. There's only one row to make 0. We have the 1 in the first row, the zeros beneath it, the 1 in the second row. Now we're going to make all the zeros beneath it. So the only thing I can do is make a combination of rows. I'm taking that existing third row and I'm going to subtract 2 of the second row. I can tell you that I made mistakes when I do this, but by having the notes on the left, that helps me catch my mistakes and say, oh no, I was supposed to subtract or I was supposed to add and I got the wrong number. So make sure you always write the parts that I'm writing in orange. That way you can reference it and move on. So now I have all 1 in the top with the zeros beneath it, a 1 here with the zeros beneath it. Now I'm working on this one and I want to make that a 1. And so I'm going to do that by dividing this row by 17. And there we have it in row echelon form. And now we're ready to rewrite it as a system of equations so that we can solve. We should know that z is already equal to 2, but let's go ahead and write it out. Writing it as a system of equations, we know that z is already equal to 2, so we just have to plug that into b. And then solving that, gives me y is equal to 3. Plugging both of those values in, we get the value of x. And then we want to write this as an ordered triple, so we're going to say x is 1, y is 3, z is 2, and you use your parentheses to write your ordered triple. And that's the solution to the system of equations. For the last 2 examples, we used something called row echelon form to solve our matrices. And if you recall, that meant the first term was 1, had zeros below that, and then the first non-zero term in the next row was 1. Again, the first term was 1, zeros below that, the next non-zero term is 1, zeros below that, and the next non-zero term is 1. This is what we call row echelon form. We now have a second definition, which is different from the first, and it's called reduced row echelon form. And when something is reduced row echelon form, it starts off with row echelon form, but it also has zeros above the ones. And so it has zeros below the ones and zeros above the 1. The only values that are not 1s or zeros can only be in the last column. You would get the zeros above the 1 by doing the same rules for moving rows around, multiplying rows, or adding them to each other. Why is something so nice when it's in reduced row echelon form? Well, let's look at video example 3. It says, state the solution set of the system represented by the matrix. And this matrix is in reduced row echelon form. Now, if I were to ask you to rewrite this matrix in a systems of equation form, that's 1x plus 0y is equal to 4. And then that's 0x plus 1y is equal to 7. Well, when I write that system of equations, it looks like the solution already. And so I have my solution, 4, 7, as my ordered pair. And so once you get something in reduced row echelon form, you should already know the solution. It's not so hidden right here in the last column of our matrix. Like the first 2 examples we did, if you're performing row equivalent operations until you have a matrix in row echelon form, then that is called Gaussian elimination. However, if you perform row equivalent operations until you have a matrix in reduced row echelon form, like we're going to do in our next example, then that is called Gauss-Jordan elimination. Make sure you know the difference between row echelon form and reduced row echelon form, and the difference between Gaussian elimination and Gauss-Jordan elimination. Question number 4 should help us see the difference between Gaussian elimination and Gauss-Jordan elimination. It asks us to redo the question that we did in number 2, but now using Gauss-Jordan elimination. Let's recall our answer from the previous time we did it. This was the original setup of the matrix. And when we were done rewriting the matrix, we had this in row echelon form through Gaussian elimination. And then recall we rewrote this as a system of equations, which we then solved. The idea is that to do Gauss-Jordan elimination, we want to continue this process, but we want to change these three elements into zeros. So let's first make the elements in the third column a zero. The only way that we can get a zero is by doing rule 3. So my plan is to add and subtract copies of row 3 to rows 1 and 2. So you can see I say row 1 minus 2 times row 3 to get rid of that 2, and then row 2 plus 9 times row 3 to get rid of the negative 9. So this is what the matrix looks like after doing those 2 row operations, and we have those 2 zeros that came out of it, and so now the only thing we have to do is make this 4 into a 0 as well. So now we're going to just do the last step. In order to get rid of that 4, we want to add or subtract copies of row 2 to row 1. And you can see that now we have all of our zeros above and below the ones, and the only non-zero numbers are in the last column. So we've now done Gauss-Jordan elimination. How do we translate this into a solution? Well, once again, we think about taking this from a matrix and writing it as a system of equations. This means x is equal to 1, y is equal to 3, and z is equal to 2. In other words, my solution is 1, 3, and 2, just like we found the first time around. Hopefully you can see that if we do Gauss-Jordan elimination and we get our matrix in reduced row echelon form, then it's very easy to see the solution without having to solve a system of equations again. And so the answer is right here, and we can just pull that answer out of the matrix directly. In the previous example, we saw what happens when we have a typical solution to a system of equations using Gauss-Jordan elimination. You end up with a 3x4 matrix with 3 1s and a bunch of zeros, and then the solutions on the right-hand side. Now what we have here looks like a system of equations with 3 variables still, but we only have 2 equations represented. So this is sort of an atypical type of solution that we're going to be finding. However, you need to know how to approach a situation like this. So when we do Gauss-Jordan elimination, which has already been done to this matrix, it has all the ones in the appropriate spots and all the zeros in the appropriate spots. What does this solution mean? It does not mean that x equals 9 and y equals 10. We have to take this and put it back into a system of equations to see how to make sense of it. And when you see it as a system of equations, it makes sense that we can't just say the solution is 9 and 10. We have some z variables in there as well, and we don't know what the z is. In fact, there's no third equation or third line in the matrix that tells us z equals such and such value. When we see a system of equations like this, what we want to do is isolate the x and isolate the y and write it in terms of z. And so then that way we will have a solution that can be solved if we know what the z value is. So there you go. We've isolated the x, we've isolated the y, and then z is just going to be z. Now how do you write this as a solution or a solution set? We know that all of our solutions should be in the format x, y, z. They should all be ordered triples. But we don't have one solution, we have multiple solutions. Because if z is equal to 1, we have a certain solution. And if I plug in a different value for z, like 3, then I have a different solution, and no matter what number I plug in for z, I could solve for a different x and y that will work with this matrix, or with a system of equations. And so I have an infinite number of solutions. I have to write them in a different way than what we normally have written them as. And so I say they're going to be in the format x, y, and z, as long as x, y, and z follow the rules that we have written down. Z has to be any real number, x has to be 9 minus 3z, and y has to be 10 plus 4z. And no matter what combination of x, y, and z you can come up with that follows this rule, then that will be part of the solution to this matrix. I just sort of want to help you understand what this means. Over here on the left, we have one possible solution, 6, 14, 1. Next to it, we have another possible solution, 0, 22, 3. We have an infinite number of solutions, so we write that the solutions are in this format, and they have to follow this rule. And so the format is on the left, you put the line down the middle, and then you put any rules it has to follow on the right-hand side, and then you use the braces for that set notation. Question number 6 is a word problem, and it states that a piggy bank contains a total of 100 nickels, dimes, and quarters, and sums to $16.50. The rest of it is just setup information, and what we want our variables to stand for, which is really important. But we're going to set up a matrix and use Gauss-Jordan Elimination to find an equivalent reduced row echelon form of the matrix, and then see what possible solutions we can find. Now it says x, y, and z are the number of nickels, dimes, and quarters respectively. And we have a total of 100 nickels, dimes, and quarters. So a total means we're going to add all of them up. So the sum of nickels, dimes, and quarters would be 100 total coins. We also should be familiar enough with nickels, dimes, and quarters to know how much their value is. So a nickel is worth 5 cents times the numbers of nickels that we have. A dime is worth 10 cents times the number of dimes that we have. And a quarter is worth 25 cents times the number of quarters that we have. And if we add up their values, then we're going to end up with $16.50. So here we have a system of equations in 3 variables, but only 2 equations, which means we'll have an infinite number of solutions. Let's write this in matrix form. And just because I don't like dealing with decimals, I'm going to multiply that second row by 100. And now I already have a 1 in the top left corner, and so I want to make the value under it a 0. And so I'm going to say row 2 minus 5 times row 1. And so this is the resulting matrix. I now want to put a 1 in the next spot. So in order to make this a 1, I'm going to divide everything by 5. I'm choosing division this time around because I notice that all of the terms are divisible by 5. If they weren't, then I wouldn't want fractions. I might do some combination of rows. But this one's nice, so we'll just divide this by 5. This is a result of that row operation. And now I have 1s in the correct spot. I have a 0 in the correct spot. I now need to make this term a 0, so I'm just going to subtract the rows. And this is a result of subtracting the rows from each other. And now I've done Gauss-Jordan elimination, and I have it in reduced row echelon form. So let's just take this matrix and write it as a system of equations. And then let's solve the system of equations for each variable. And then let's just say that z is equal to z. We are asked to find 3 possible solutions. So we want to plug in some values for z, and then find the resulting x's and y's, but we can't just find any values. Once again, we have a word problem and we have to make sure that it makes sense. So some values that would not make sense would be to have a negative amount of dimes. You can't have negative 5 dimes. So you want to make sure that all your answers have positive or 0 integers. It wouldn't make sense to have half a dime either, or half a nickel. You would want to make sure that they're all whole numbers or integers and not any fraction answers. So as long as we follow those parameters, our solution should be okay. The question doesn't ask for it, but I'm putting in here the rule for our solution set. It's any ordered triple where x, y, and z have to be positive integers, and then x and y follow the rules that we came up with. I just want to make sure that we understand what the solution set should look like. Now let's come up with 3 possible solutions. Now when I plug in z is equal to 10, notice that my x is equal to negative 100 and y is equal to 190. And that's not possible because the x value is a negative value, so we'd have to throw that solution out. Let's try a different value. But when I plug in z is equal to 50, then my x is equal to 20 and my y is equal to 30, so that's a valid solution. And because it's a word problem, when we find the solution, we have to put the right units on it. So this would be 20 nickels, 30 dimes, and 50 quarters. Let's come up with another solution. If I plug in z is equal to 45, I get x is equal to 5 and y is equal to 50. Those are all valid values as well, so we can count that as one of our solutions. And so that would be 5 nickels, 50 dimes, and 45 quarters. And let's find one more solution. And when I plug in z is equal to 55, I get x is equal to 35 and y is equal to 10, which is also valid values. And that translates into 35 nickels, 10 dimes, and 55 quarters. And so we've come up with 3 possible solutions for this. Why don't you practice finding one more solution on your own? And that's it for the section, but that was a lot to take in, so make sure you get some practice in, make sure you do your homework, but pay attention to the words. What does row echelon form mean? What does reduced row echelon form mean? What does it mean if I ask you to do Gaussian elimination? And what does it mean if I ask you to do Gauss-Jordan elimination? And what do the solutions mean? And what units are you going to put on the solution? These are all questions that you need to be able to answer when you're doing this type of work. All right, thank you, practice, and have a wonderful day.